Returning to some chemistry that you're already familiar with, if I ask you to draw out the mechanism for the reaction of some random double bond with HBr, what you would start is by saying, hey, the double bond is going to serve as the nucleophile, and it's going to do so in a 2-electron process, which then breaks the HBr bond and leads in the intermediate stage to a cation, and you're going to choose to put that cation at the tertiary position, and you will have made a new carbon-hydrogen bond. And so this primary position now has 3 carbon-hydrogen bonds. That leaves a plus at the tertiary position. So this is what we end up calling the Markovnikov product because you go through the formation of the more stable carbocation. And so you have the Br minus, then it goes ahead and adds. The end result of the reaction is that you have now added HBr across the double bond, and you have done so in the Markovnikov sense. So if you simply allow the double bond to react with HBr according to 2-electron processes, then you end up going through a carbocation, and it is the carbocation that decides the regiochemical outcome here. The choice between a carbocation at the tertiary position or the primary, obviously the tertiary position wins every time, therefore this is the product that you get. And again, Markovnikov simply said you have to go through the more stable carbocation intermediate. So the reason why I bring that up is because we're doing this now under radical chemistry conditions. And so again, we have HBr present, but now we have some kind of radical initiator, and we are explicitly hitting this with a light to kick off the reaction, or maybe we're heating it up. Any other form of radical initiator would also work here, say AIBN or something. Once you create a radical type mechanism, then you're going to lead instead to the anti-Markovnikov product. You're going to put the bromine on the primary position. You're actually going to do the addition essentially in the reverse order. And in order to understand why that happens, you need to think through the mechanism of the anti-Markovnikov addition. But it all starts by recognizing that you have a radical initiator present, and so the first step of this mechanism is going to be the initiation of the radical chain. And so what happens is that this peroxide or AIBN or whatever other initiator you have fragments on its own and creates radicals, and then you have a second initiation step. This radical will then react in a radical fashion with the HBr present, and that will be a second initiation step, and what it will do is create for you a Br dot. So the result of reacting RO with the HBr is that you now have formed an alcohol, and you have also formed a Br dot. And so the key feature of this mechanism, the one that drives this, the one that explains the regiochemistry, is the presence of this bromine as the propagating radical. So now let's imagine what happens when our bromine encounters the double bond that we are trying to react with. So now the Br dot is going to react with this double bond, but what we do is we first install the bromine, and then later we come by and install the hydrogen. And that explains the anti-Markovnikov feature of this reaction. Since it is the bromine that's installed first, the remaining radical, the leftover electron, will occupy the tertiary position because that's more stable than the primary. So essentially what's happening is you're reversing the mechanism. In the original mechanism, the double bond attacked the hydrogen first, which then created both the Br minus and a cation. Here, however, the double bond gets attacked by the bromine radical first, which then installs the bromine already, but leads to the more stable radical. The radical then encounters HBr and reforms the propagating radical. So the radical makes a bond to the H, which also generates again another Br dot. The key thing to recognize, of course, is that the propagating radical is the bromine species. This is the thing that is getting used up in the first place and reacting first with the double bond to create the radical at the tertiary position, which eventually leads to the desired outcome. And it is the propagating radical that is regenerated in the second step. So once again, propagating radical simply means it is used up in the first step of your chain, regenerated in the second step of your chain. And then, of course, termination products are going to be any two radicals encountering each other. So, for example, 2 bromines could encounter each other and make Br2. You could have 2 of these tertiary radicals encounter each other. For example, if this radical here were to make a bond to this radical here, that would also lead to a termination step, and it would be a bizarre one. So there are many such termination steps, and I've only illustrated a couple of them. The upshot, though, is that you can add HBr across the double bond in an anti-Markovnikov fashion. Because, again, what happens is that you install the bromine first, and that leads to the more stable radical. So whatever gets installed first will then lead to an unstable intermediate. So if you install the hydrogen first, you have an unstable cation, which then gets filled by the bromine. That's the Markovnikov product. If you install the bromine first, that leads to the unstable radical, which then reacts with HBr in order to make make the final product. Again, the order of addition is what matters. Markovnikov products come from the most stable possible cation. The anti-Markovnikov product happens only when you have some radical initiator, and it relies on forming the most stable radical. The addition happens in a different order. Bromine adds first, more stable radical forms, that more stable radical then abstracts the hydrogen, and that leads to the observed products.